So I'm back finally. I'm so sorry for the long delays. It's been pretty much mayhem the past weeks. It's been pretty tough. But now I think I'm over the hill and things are looking up, and now I'll be churning out lectures as much as I can and spending my time doing recordings. Um, I also found a piece of green cloth that I've put as my background so that I got the green screen. And as you can see, I have an interesting background. What you see behind me is a tribute to John Conway, who unfortunately passed away, 82 years old, from the COVID-19 virus. If you don't know who he was really one of the most inventive and original mathematicians of this of the past 50 years, and he did loads of things. Many of you probably know him from Conway's Game of Life, which is a cellular automaton that he invented, but that's just a tiny little thing of all the fantastic brilliant ideas he had. So that was very, very sad. Today we will talk about the mailbox processor. And this is it's not really a part of F sharp, but it's part of the F sharp standard library, and it's a very, very, very useful device. And you will see we will actually be utilizing this thing. We'll talk about it in this lecture. We'll talk about it more, one application of it next lecture, and then as we get on to web programming, this will be absolutely central to how we do things. And now that we have continuation passing and async under our belt, this is really putting that technology to work properly. So let's have a look what this is. So at heart, what lies behind this whole idea is the actor model. And if you're not familiar with the actor model, it's a general mathematical model for doing computation. It was invented sort of largely by a guy named Carl Hewitt, and he sort of looked at particle physics and how got his ideas from particle physics, and how various types of particles communicate by sending out photons or virtual photons and so on, to convey that they exist, and the forces. So that was his idea. But it turns out that this is a very general way of doing computation, but in particular useful for concurrent computation. There's a whole lot of mathematical theory behind the actor model. So if you're so inclined, there's a deep and rich literature about this. But the idea is very simple. And that's what we're going to exploit. And it's basically this. An actor is an entity which can communicate with its world only through message passing, by sending messages to others and receiving messages from other actors. Sometimes these actors are called agents. And this is it. An actor sends a message to somebody and they will reply, or they can spawn more actors, and those actors might send a message back. They can perform side effects and so on. So they can do all these things. But an actor is this little module, this little object that sort of sits there and with its own internal state and its own internal life, and it responds to messages from the outside, and it can send messages to the outside, and that's it. So this is sort of a pictorial representation of how it works. So each of these twirly things here are actors, and an actor can send a message to a mailbox, which is, and then another actor will sit there and wait for messages to arrive in its mailbox. And as a message arrives, it will pick it off. It will do some computation. It will perhaps have its internal state, and when it's done, it will send off some new messages to some other actor, so maybe reply back to the same actor that sent the message to it, depending on the situation. The important thing here is the mailbox, and that's the sort of technology that we're going to be talking about, because that's a message queue. So as messages come in, if the actor hasn't done its computation and isn't ready with it, the message will just sit there until the actor is sort of ready to receive it. So this forces a sort of a serialization locally within the actor. Now it's very easy to parallelize this, of course, because you can just have multiple actors and just send messages to all of them, and they will sort of pop them off and do everything in parallel. So that's the sort of basic idea of the actor model. So why is this useful? Well, one of the things is that using this idea, it's very easy to decouple components of the system, since the only way they can communicate is by sending messages, and those messages have to be well defined, and that's basically just sending data. So you don't make any function calls across boundaries, you don't do any of these things. You send a message and you get a reply, or something else happens. Maybe it does some IO, maybe it dumps stuff to the database, who knows. And this is sort of very much in tune with what is called the single responsibility principle. Another thing that you can do with these things is to have shared data without locking. And there are plenty of examples of this. I considered showing one, but I thought, well, why bother? We'll look at some other features of this. But this is typically a problem when you're doing multi-threaded things in traditional languages like C# or C++ or Fortran or whatever, is that you have multiple threads and they need to access the data. And if they are sharing the data, which they probably will be sharing some data to be able to communicate, somebody's going to have to lock it. And this is very harmful performance. And these mailbox processors can help deal with that in a very nice way, and you don't have to do any locks. And you can just send off a message and you can continue doing whatever, and things eventually will get updated as the messages gets popped off the queue. So this provides pretty much safe communication between threads. The one thing that we're going to be looking at in some detail is avoiding mutable state, because this is the one property that we're going to be interested in and using in the coming lectures. As you know, we don't really like mutable state very much, because it's causing all kinds of problems with referential transparency and so on. So, but sometimes we need to have some kind of mutable state, and using these mailbox processors, these agents, we can encapsulate the state inside this agent, and it will just sit there and recursively keep it in flight all the time. And so this provides a very good way of dealing with that. And the third thing, or the last thing, is robustness, which is not something I'm going to go into, but if you go and look at the language like Erlang is largely built around this idea. So that this is the central idea of the Erlang language, and the OTP protocol is to have these actors and message passing between them. So in Erlang, you have objects. Erlang is a functional language. It abhors mutable state, but you have these modules or objects in Erlang, and the only way they can communicate with the world is essentially by message passing, and then they have a special protocol for it. And using this technique, Erlang is able to achieve like ridiculous robustness in certain situations. Ericsson has claimed that some of their systems have a reliability of 99.999997%, which is pretty good, really. So Erlang, fantastic, super interesting language. Highly recommend learning Erlang and checking it out. One cool thing with Erlang is that the actors in Erlang, they are actually across process boundaries, and they actually even across machine boundaries. So in Erlang, you can have these actors that sit on different side of the globe, and you just say, well, just send a message to this actor, and you don't really have to care where it is. It can be, you can be in Tromsø and the other actor is somewhere in Sydney, and it just works. You don't have to do anything special about it. Another super interesting language, and I highly recommend learning, or at least looking into, is a language which in its current incarnation is Smalltalk 80. It was sort of set in 1980, and you might think that, well, old crap, but it's not. Really interesting language, and very useful, and it has been used successfully in very complicated projects. In Smalltalk, everything is an object, and some consider it the only sort of real proper way of doing object orientation. Everything is an object, and objects communicate. The only way objects communicate in Smalltalk is by message passing. So they send messages to each other. Very fun language to program in, and it has a fantastic IDE. Like Smalltalk had an IDE back in 1980, which is probably superior to most of the IDEs you find today, believe it or not. It's ugly, but really great. Other examples of message passing systems, agent systems that you can use is RabbitMQ, which is a really sort of a advanced message queue. It provides persistence, all kinds of things, multiple queues, and you can do all kinds of really fancy stuff with it. It's sort of an incarnation of something called, which is AMQP. MQTT, which is very popular with IoT people, also a great little thing to use. And if you want to do actor-based stream processing, then there's akka.net, and which originated in the Scala world, and there's a .NET implementation of it, and Microsoft has something similar called Orleans. I don't really have a lot of experience with those systems. I never needed anything quite that heavyweight, but it's good to know about. So let's have a look at the F# mailbox processor. So it gives us lightweight, and I mean really lightweight, actor-based programming F#. It's just a simple message queue, so that you can easily post messages from one part of the program into this queue, and it will respond in whatever way you want. Everything here is asynchronous, so this is where this async comes in. But, and here's an important thing, it's serial. So the queue is serial. So which means that as messages come in, they will get processed in the order that they arrived. Which means that as the mailbox processor picks a message off the queue, it will, although everything is asynchronous, it will still run the whole thing and get the result and send a reply or do whatever it wants before it picks up the next message, right? So this is important. Okay. It's super lightweight, so you can have thousands and thousands of these. These are much cheaper than system level threads or things like this. Like these things cost a few thousand bytes probably. I don't know exactly how much. In Erlang, it's pretty extreme. In Erlang, one of these things cost like 300 bytes to set up. It's nothing, right? So you shouldn't think that, oh, I need a mailbox processor and that's a sort of heavy thing and you should have only one in your program. No, you can have hundreds and thousands. You can spawn them off as much as you like. You don't have to think about it even. It's cheap, and they're very efficient. But one thing you don't have in this thing is like if you go for RabbitMQ or one of these advanced systems, you can have persistence. As soon as a message comes in, it will save it to disk in case things crash. You have your messages saved. That you don't get with the mailbox processor. So this thing is just like any other function call. If your system crashes in the middle of a function call, everything is lost. So this is not like keeping your stuff anywhere. It just exists and it's gone. And one other important thing here is also compared to Erlang is that this F# mailbox processors, they don't work across process boundaries. So they are within this one pro instance. So you can't send messages from one process to another. That's not really a major issue. So let's have a quick little look at how these things work. and at first, when you look at these things, they might be a little bit mind-bending, but it's quite simple. So let's have a look. So let's define an actor. So say let actor, and then I say mailbox processor start, and start is a function which takes a function. So it's a higher order function. So it takes a function with one argument, which is an inbox, which is an instance of a mailbox async message thing. It's an object. It's got some properties on it. And then we have internally here a recursive loop thing. Now, I don't really have to have that. But if I don't, this thing will wait for one single message and it will just exit. And it won't be sitting there waiting for messages to arrive to process them. It will wait for one message and it will be gone. So that's why I have this infinite loop. You could, if you want to have something that loops for 100 times, well, fine, do that then. But the typical way to do this is that you have this inbox. You define a recursive function which returns a async computation, and it will come in, it will call inbox receive, and then it will block. It will just sit here and wait until somebody posts a message to it, and then inbox receive will hand off the result of the receive, and here we just print it out, and then you just loop back. And then the last thing we do is we just start this infinite loop before we exit. So what will happen here is that this mailbox processor will start. We will start this thing, and it will just keep on looping. And the actor will just sit there. And most of the time it will be in a blocked state. And the way we can post things to this is we just say actor post 42. And that will send the integer 42 into this code. It will print it and wait for another integer. So this is not particularly interesting, but shows how it works. Here's so if we go back. Oh yeah, no, I didn't have any state in this one. So this one just does some I/O. It doesn't do anything. In the demo later, I will show you a case where I have some state. But here's another example. It's pretty much exactly the same example, except now I keep a state between calls. And I don't have an immutable state here. And the way I do it is that I let this loop keep this state variable. So I say, well, loop, and it takes some state. I could call this x as well. And it will do the same thing. It will sit here and wait. And then it will print the number it received from the post. And it will print the state. But as it loops, it will now feed in the new state, which is, in this case, it will take the n and add it to the current state. And now I just initialize this infinite loop with 0. So now it goes in and the state is 0. Sits here, I post 42. It will print 42, 0. And it will go back, and now the state will be 42. So this is the way that you can get rid of mutable state. I'll show an example in the code session in a little while. I'll show how to actually get the state out of this thing if you want to sort of have this thing keep your mutable state without using mutables and then extract it. So a third little example. This is how to do that. How to actually get a reply back from the mailbox processor, and this is tiny little bit more involved. So here we just do the same thing. Start the mailbox processor. We give it this inbox function. Fire up a infinite loop. This time again, I don't have any state in this example. And now I say inbox receive, and then I have this. This time I just say, well, the thing that this will receive will be a tuple, one which I have called reply, and then the n. And this reply I will set up in such a way that it's actually a reply object or reply channel, so that I can send a reply back to the caller. So here I then just say reply n+1, and I loop. I don't save any state here, anything. This is just the agent-based add one. So kind of complicated way of adding one to an integer, but sort of drives home the message. And the way we use this is that say, okay, fine, I will just say, well, okay, let x is actor, and then instead of saying post, I just say post and reply. And post and reply will take a function as an argument, and the first argument of that function will be this reply channel object. And then I say, well, okay, post a tuple reply, 42, which is the same I will receive here. So I can use, we'll see a later example where instead of using a tuple, I will actually use some proper messaging and use a union type to distinguish between different types of messages. So this should be fairly straightforward. All right, so let's have a look at some code. So here I've already set up a little example. So let's do the first example here and see how it works. So here's pretty much the same example I had in the previous, the first example I had on the slides. Set up a mailbox processor. We can look at the type here and see that the type is a mailbox processor of type int. It has inferred that automatically from the posts down here. And now I've actually added a mutable state into this thing. Say, well, loop. And then it will receive, it will print the number it received. It will print the current state. It will update the state, and it will loop. So let's see how this thing works. So we can do like this, and we'll just pull this up a bit here. So now we see here what happened. I sent the code to F# Interactive, and it prints received 1, state 0. And now I can do a post this guy, and it says received to state 1, which is the state that we had from the first thing. And now I can say, well, okay, for 57 received state 2, post 0, state 57. So this is oh, maybe I should increase the font size a bit. All right, that was better. I think one notch more. Yeah, this is good. Right. So this just shows that how we post things, and then I have the same example over again, but this time using instead of having a mutable, I have the state in the loop. So let's try this one, actor 2, and I'm just gonna post both of them at the same time and look at this. And yeah, so we see received 3, state 0, received 4, state 3. So we can see that the 3 I sent in here, it received, is now become the state, and that's how we can get rid of. That's how we get rid of the mutable, which is always nice. So let's do another one. Yeah, I had to add a slightly ugly slightly ugly type annotation here for my tuple, which has the reply channel and the int. But this is pretty much the same example that I had on example 3 in the slides. So here we say, okay, fine, here I have the state is in the loop, I don't have any mutables, and I will just receive, instead of just receiving an integer, I now receive a reply channel and an integer, and I reply to that, and then update the state or loop. And you will see how this goes. So let's send this to F# Interactive and have a look. So here we see that I do post and reply, and then I say print reply. And I first reply is 0, which is the state that it was in, and the next time it prints reply 21, because that was the value I posted, 21. And if I would call it once more, do it like, oops, oh, interrupt, that wasn't what I wanted. Oh, let's see, I can go up here instead. That was, now I got the reply of 63, since it keeps adding the numbers. So let's have a look at the code again. All right. So yes. So here it always takes the previous state and adds the number I posted in this example. Okay. So let's have a look at how this ordering, that everything that actually is going on here is that things don't happen out of order. You really do get this ordering, and everything has to complete, even though this loop here inside this mailbox processor is asynchronous. It really has to wait for each message to come through. So let's look at example 4, and here I have used the mutable state just for a little bit of variation. I initialize a random number generator that will generate an integer between 0 and 1000, and then I say, okay, loop, and here I will print the state, the mutable state as I come in. I will update the state, I will sleep some time, randomize time, and I will print the out state, and then I will loop again. And then I will just post 3 messages, and then sleep for some time, and then see what's going on. So, oops. So let's send this to oh, not defined, so I need to do like that. Sorry about that. And then we'll send this thing. All right, here we go. So now I can run this test 4. And what I want you to note is that it will sleep about, well, on average it should sleep about half a second or so between each of the posts. So you should see, in principle, there should be something like a second, 1.5 second, 2 second delay between start and send. And then it will sleep for 5 seconds, and then it will print done. But let's see what happens here. Okay. What? Oh. No. Oh, test 4. Sorry. There we go. And you saw one thing. It prints in 0. Oh, so this is some problem with F# interactive. But one of the important things that you should note here is that it printed start and sent almost instantly. And this is because all of these things are asynchronous. They post their thing to the mailbox processor and they return immediately. And then the mailbox processor will take these messages in this order of 1, 2, and 3 and process them. Unfortunately, the printing didn't work quite here. So that was a little bit a bummer. I can see if I can run them in the terminal instead. Yes. So this is the important thing. It posts and it just continues immediately. There's no waiting at the post stage. If you do post and reply though, then it's going to have to wait for the reply to arrive. So then it will block until the reply comes through. So this is really good for you just fire off and forget. You go on and do your other business, and things will happen eventually. All right, so let's look at example 5. So now in this example, I will be using just pretty much the same example again, but instead of using a tuple for reply and so on, I'm actually using a union type to distinguish between message types. And this is a very useful technique that we will be using not in the next lecture, but after that. So let's look at example 5. So here I have defined a message type. It has two different types of messages. It's just a union type with a set, sets an integer, and then it has a get of async reply channel of int. And then I'm just doing the same actor 5, sets up an inbox, mutable state, but inside this async it will do a receive and match that receive with the set message, and if it's set n, it will set the state to n plus state, and if it's get, it will reply with the state. So we can have a look. And then in this test 5, I've used I just used a list to generate these things to send them off. And then it will generate 3 different posts with set messages, and then I will call this actor and get the reply message back and print the result. So let's see how this works. There we go. That looks fine. Let's say, okay, let's make this a bigger. Test 5. And there we go. And it says done 6. Now I didn't put in any delay, so this is sort of everything happens totally instantly. But there you see, I added 1, 2, and 3, and if you add 1 plus 2 plus 3, you get 6, which is the reply. So here and this is actually using this union type for various types of messages. That's the sort of the key element in the so-called model view update scheme of doing reactive programming that we'll be looking at in the next screencast. So the final example, and it will be here, and let's look at. So yeah, so in this one I will pretty much do the same thing I did in example 5. So I'll be using the same. I'll just be using the same actor 5, but now I will actually do this. Send in these messages in parallel, so I will just bombard it with messages in as fast as I can. So here's This I should actually, yeah, I should. Let's put in something like 7 and then have it actually get the result out. So here I've added a little helper, post async, which will just do a set n message and then post it to this actor, and then it will just print the result. So let's see. Let's have a look at this. Right, and then we just run test 6. And there we go. And it's instant. And the thing, I should probably have put in a little bit of sleep in this, but it wouldn't have mattered. The thing is, it doesn't matter if you post in parallel or not. Messages will arrive, they will get processed, and that's it. It doesn't speed up anything at all. There's really no need to do that. So that's this sort of having this sort of trying to force some parallel processing here it's not going to happen. The mailbox processor itself is forcing a serialization internally. So if you want to have things being processed at much faster speed, then you need to create a number of these mailbox processors that you can post to. Yes. So that was pretty much it for today. Tomorrow we will look at the model view update. That will be a little short quickie. It's sort of the basis of how we do web programming or web interfaces in F#. It's a very convenient and very practical model of doing things, and of course we completely avoid having any mutable state in our code, which is a huge bonus and makes things very nice and reliable. So until tomorrow.